Hello, everybody. My name is Timur Bashirov, and welcome to the webinar Getting Started with the Exabyte.io platform. Today, we'll speak about how one can get started with the platform. And before we start the presentation, let me give you a couple of notes. First of all, the goal of this seminar is to help people to understand the main concepts behind the Exabyte.io platform. This is the first webinar in a monthly recurring series. So first Friday of each month, and then third Friday of the month. The December seminar will be a little bit different. We're going to be doing it on the fourth Friday because of the holidays. Every participant should be a registered Exabyte.io user. Every participant will receive this presentation in a PDF format after we're done. And highlighted text inside this presentation will contain links to web pages, to documentation, some figures and links as well. The webinar is recorded and will be made available online. All information contained here is also at docs.exabyte.io. At any time during the webinar, if attendees have any questions, they can ask them using the chat window. So this is how the Zoom session should look to you. You should be able to click on the chat panel using Zoom toolbar and then ask questions using the chat. Okay, we will look through this chat panel as we go during the presentation, over the presentation. We will assume that the users are exploring the Exabyte platform and would like to learn more about its vision, capabilities, and hands-on, with a little bit of a hands-on demonstration of the features. And then we will assume that the user is familiar with the basics of computational material science, file formats, modeling techniques, and such. We will also take the advanced topics outside of the scope of the seminar. And that includes command line usage, programmatic usage with RESTful API, and an overview of the computational infrastructure and such. So that will be covered separately in the advanced topics webinar. Everybody here, all the registered webinar participants, have access to the webinar account. And this account has the balance allocation and advanced features enabled for it. During the webinar, to save time, we'll be using recorded videos of the functionality, but all the attendees can follow the presentation or the PDF on their own time and use the webinar account to perform equivalent actions as the ones that I will be demonstrating today. Accessing the webinar account can be done by clicking on the username in the right-hand top corner to open the right-hand sidebar, and then clicking on My Accounts inside the right-hand sidebar, and then choosing the webinar by clicking on its name in the table. Okay. So once you do that, you'll start using the platform under the webinar account. This is the brief agenda for today. We'll speak about the platform capabilities for about 15 minutes or so, and then we'll review the core parts of the platform for another 15 minutes, and we'll finish with the Q&A session if there are questions. And then we'll continue to speak more about specific entities involved inside the platform, like materials, workflows, and jobs, and how to execute basic actions on them, like uploading, importing materials, or creating workflows, sub-workflows, running jobs, and such. So, excuse me, let us start with the Exabyte platform and its overview. What is the Exabyte platform? We envision it as a digital ecosystem that brings together experts with backgrounds in many different scientific fields. The platform that is collaborative can facilitate multi-scale simulations, scalable computation, data-driven machine learning, artificial intelligence practices. And naturally, when we have to have multiple people and multiple simulation techniques, we start with the cloud, not necessarily public cloud computing platforms, but cloud as the focal point that is able to connect all these different people, different techniques together. And that's essentially what we demonstrate here. We have computational scientists, experimental scientists, data scientists, all collaborating in the cloud. And we also have IT administrators and management, R&D management, able to see what is happening and provide their feedback. We speak about a multi-scale toolchain that consists of in-house, commercial, or open source simulation tools that all contribute into a data platform. Organized data that can be searched and analyzed and can lead to the creation of machine learning, artificial intelligence techniques. And of course, all of that has to be secure. So the collaboration that doesn't need anybody else to be involved in it still happens in a secure private space. So how do we implement something like that? We start with the open source components, and we start with the data standards. We develop and maintain a set of open source components that together form the foundation for a fair R&D ecosystem. And fair here stands for findable, accessible, interoperable, and reusable. That's an acronym. The data standards, we identify 4 different kinds of entities globally and multiple other kinds of entities, less important. So the 4 key entities are materials, simulation workflows, calculation jobs, and material properties. And we all of these entities are implemented in object-oriented extendable way and separated on purpose. In many cases, when we run simulations, we do not separate the information about the simulation workflow and the material structure, and that leads to confusion and a lot of problems along the way. So we separate this information and these entities on purpose and create different data structures. These data structures are implemented as JSON schemas and are published online on GitHub as an open source repository that we welcome other people's contribution to. We call it SC for brevity, exabyte source of schemas and examples. We also provide extractors that help convert the data from other existing sources, like existing density functional theory, simulation engines, to SC, into the JSON schemas and standards. And that is another open source repository on GitHub with examples for density functional theory. And finally, here in this picture, we have applications that allow users to utilize their data formats to create and edit materials information. And there's an example for solid state materials design, materials designer, as we call it. It's a 3rd repository on GitHub here. And the same component is used as part of the Exabyte platform online. So this application is part of the greater Exabyte platform, as well as other things like the extractors that we discussed before, computational tools, the computational scientists that come in as users and produce information using the tools, the familiar tools to them. We also have RESTful API that can take the converted standards and store them in database, the information in converted standards. And we have other people that through the applications are able to communicate and see the results of the computational science. So all these components are built into a publicly accessible online platform at platform.exabyte.io and can be licensed and further deployed in private cloud scenarios as necessary. And we start with the computational material science as the most well-known scenario to us. However, there are also a capability to add data science workflows as of right now to build machine learning and artificial intelligence. And then we can also add experimental validation into the platform. And today we already allow experimental scientists to see the modeling insights to provide their feedback. So there are multiple types of users, including data scientists, experimental scientists, and computational scientists that we identify inside the platform. And usually these kinds of users have their own external elements that they work with that are independent of the Exabyte platform. And we provide support for those external elements too, like external data platform tools, external laboratory equipment, and computational clusters that people deploy outside of the Exabyte platform. So when we speak about the materials R&D cycle, there are multiple steps involved in it, and Exabyte platform is unique in a way that it is the end-to-end platform that covers multiple different parts of the cycle. That includes designing material structures, that includes designing modeling workflows, includes provisioning high-performance computing infrastructure, controlling and asserting the completion of the calculations, collecting and organizing data in a structured storage, building data analytics and artificial intelligence tools, and feeding experimental validation, number 7 here. So I was just going over the circle. All these components, except for number 7, are present in the platform today. And I'm going to demonstrate to you how they work right now. So this is an example account page inside the platform. As we can see, there are all the entities that we just discussed, like materials, workflows, and jobs, that are organized. And we can see which materials, which workflows, and which jobs this account had just created. And we can see there are multiple users that belong to this account, multiple people. And all of them can collaborate and edit and organize all these entities. We also see some basic information about this account and computational infrastructure that is accessible to it. Like these clusters, one of them is on Amazon Web Services, the other one is on Microsoft Azure, and some parameters of this computational ecosystem as well, infrastructure. So step number 1 of the R&D cycle is the creation and design of material structures. And here is a quick example how we can design and adjust and work on an aluminum gallium arsenide surface here. We can store this information and tag it to be able to find it easier in the future. A quick demonstration. We can also set up and create chemistry, meaning that we can create images that correspond to different parts of the chemical reaction. So if you look at this, we can see that there is a hydrogen atom that moves inside this barium strontium zirconate matrix. And depending on where this atom is, we can see that there are different configurations that we have just created. There's an initial configuration, and there's 0, 1, 2, 3, 4, 5 steps along this path. This is usually helpful to understand chemical reactions. Now, once we do have the structure set up, we can use the simulation workflows that we have pre-created before, or other people have shared with us, or using the templates that are available in the platform for pickup. So here, it's just an example, list of workflows: electronic band structure, phonon calculations, total energy calculations for density functional theory. And we select those workflows to apply them to the materials that we have created in step number 1. And here we can also select the infrastructure, the computational infrastructure that we would like to run these calculations on. And we have the flexibility of running it on multiple cloud providers, multiple different kinds of computational hardware. Okay, so, and at the end, we have created a simulation that includes the material, the workflow, and the computational infrastructure parameters. The next step is to execute the simulation, as this video demonstrates. We track its progress, make sure that all the components of the simulations are executed successfully, and at the end we get the result, which in this case is the electronic band structure. Or when we deal with chemistry, it's a reaction energy profile calculation that shows us the energy along the reaction path. Now, multiple people, especially those who are experts in the field, prefer to use programmatic access to this functionality. And that's something that we support as well. So on the right here, I apologize, let me restart this. So on the right in this video, we see a Python script, a Python environment with a bunch of directives. On the left, we see the web application. So what happens is that from this Python environment, we do things like import materials by the ID. So we give it ID from materials project in this case, and the materials appear inside the platform based on the code that we execute. And then we start set up and run the calculations, again, purely from Python in this case. Wait for the calculations to complete, as we see here. And when the calculations are complete, indeed, we extract the information in a form of a spanless data frame. So it contains things like initial lattice parameters, initial IDs, initial names, and then final lattice parameters after the relaxation, pressure, as you can see, band gap, and other properties that are of interest to us. Okay, so this is just a quick demonstration how we can programmatically control the calculations and extract the data. And to take it to another level, we can also run Jupyter notebooks. As you can see here, we start a Jupyter application, and then click on the notebook icon to open the notebook sessions. And then we select one of the Python files to edit it, or we select the Jupyter notebook itself to open it, and we run it. We run all of the cells. In this case, what happens is that we have a query that we apply to all the materials owned by this account. And at the end, in step number 5, we see the output of this query. So all the materials that contain silicon, as the query has, are printed in step number 5. So these are the quick demonstrations of steps 1 to 6 through 6 inside the R&D, digital R&D cycle. A little bit about the applications that we support. We support density functional theory engines, both pseudopotential and local orbital. As of today, molecular dynamics engines like GROMACS and LAMMPS, analysis tools like BMD, Vestex, Kristen, and such. There is support for all of these tools that is available in command line as well as remote desktop. So people familiar with batch scripting will be able to use the platform through command line tools as well, and modules environment. Here is a quick demonstration, so we can navigate online, open the terminal through the web, and then navigate into the directory where we'd like to run the calculation, adjust the job script. In this case, I'm putting the right number of processors, or ppm directive, and then I submit the calculation, check for its statistics, and then at the end, when the calculation is done, I do some command line logic to be able to extract the properties from the calculation file. Okay, so here is the midway summary. Exabyte.io is a comprehensive ecosystem for materials and chemical R&D that is transitioning today's prevalent isolated or siloed approach to a fair, findable, accessible, interoperable, reusable infrastructure instead. The goal of the platform is to supercharge computational scientists to accelerate their work and connect multiple units together, including data science, computational science, and IT. Today, computational material scientists are focused on delivering the insights about materials because that's how they are judged, depending on their progress along developing new materials. And they usually minimize any time spent on building software tools. And this leads to this disconnected and isolated approach. However, with the advent of machine learning, the availability of materials data, we now have to incorporate those techniques into day-to-day workflows for computational scientists, and that calls for the transformation. So Exabyte Platform provides a flexible foundation that can be adapted to the needs of the customer organizations. You can think about it as an SAP or Atlassian deployments where the companies provide the foundation that can further be modified in a very, very flexible way to fit the customer needs. And finally, the platform can be accessed in multiple levels, including infrastructure for computations only, and programmatic level, and the web interface, of course. So The following are the core parts of the platform that are helpful to understand its purpose. Let's start with what's under the hood. We look at the diagram of the ecosystem that we spoke about before. We'll see that there are extractors, standards, and applications. And if you look at Exabyte.io GitHub page, we can see repositories that correspond to each of these items there. So FC, for example, corresponds to the data standards. Exaparser corresponds to extractors, and materials designer corresponds to the application. And there are also examples for RESTful API, as number 4 demonstrates here. So go online, visit our Exabyte.io GitHub page, and you can see all the code available there. As I mentioned before, we identify key entities that we work with inside the platform, and those are materials, workflows, jobs, and properties. If you look at this diagram, we can understand how they are connected with each other. So we have materials that have certain properties. Some of them exist before the calculation or execution of the job. Some of them exist after we execute the job, as we can see here. And there is a workflow that also possesses multiple properties. When we take material and workflow together, we form a job. And then when we execute it, we extract a property, which also is extracted with a certain precision. So material and workflow together form a job delivers a property. These entities are separated on purpose to improve their modularity, cover multiple model types, material types. And this is work in progress. Sometimes the boundaries could be blurry, but the data structures are very well defined. And they're defined based on JavaScript object notation format, JSON. Data structures are organized as schemas that define the data component relations and implemented inside this open source repository on GitHub. This repository represents a Python and JavaScript package at the same time. So it's an NPM package, it's a PEEP package. So it can be reused in JavaScript and Python projects easily. And we welcome other people's contributions and helping us extend the set of standards. So here's an example schema on the left. We see that it contains certain properties, such as formula, basis, lattice, and such. And here is an example of a material structure corresponding to silicon. In this case, we can see basis coordinates and elements that correspond to this coordinate IDs. Silicon. Why it's important to understand the data structures? It's important to understand because these data structures, they power the work of the user interface. So if we look at materials list inside the application and then choose expand action, then we will see exactly the data structures that we just reviewed. So this is an example material, strontium zirconium oxide, and its data structures contains the basis and lattice according to the format that we just discussed. So every entity that user encounters inside the Exabyte.io platform is defined inside the Exabyte data convention and available online as an open source GitHub repository. These definitions are meant as a unified format, able to incorporate data from multiple materials types, crystal, molecule, nanostructure, etc., and multiple modeling approaches as well, including density functional theory, molecular dynamics, Monte Carlo, and others. The platform provides a user interface to work with these entities. However, they can also be accessed through command line, remote desktop, or RESTful API. People who are familiar with the GitHub or software development workflows, they can contribute to this remote repositories. And here's an example pull request. So here's an example contribution coming from a third party into materials designer application. We will go over the code review, go over the pull request here. And once we converge, we'll take the code base and deploy it online so you can use this feature inside the Exabyte platform. We have created the foundation that can be built upon to incorporate other material types, modeling approaches, and properties. There are multiple components of the Exabyte platform that are open source. It can be extended. Users may edit the code to implement desired functionality and put a pull request on GitHub. We will review the code, incorporate the changes, and reward the contributors. Now I'd like to speak a little bit about the user interface. So here is the user interface as it presents itself to the platform users. There are 5 key components. At the top, we see there is a header. On the left, the header can be used to open either left-hand sidebar or the right-hand sidebar. There is a footer that contains links to documentation and additional information. And there is a support widget that allows people to submit support requests. So let's start with the support widget here, because most of the time, people who start with the application with using the Exabyte platform do have questions. So when you do have questions, please use this support widget to submit a ticket. Indicate your name, your email address, and how we can help you here. And what's important, we ask everybody to include together with the explanation, to include screenshots or screencasts of the problem, because that gives us a much better way to understand your problem. There is also a chat that's available for users that are not yet registered inside the platform. Sometimes it could show when you navigate or log in into the platform, it could show up for the logged in users too. And we discourage its usage for the people who are already inside the platform. It's only meant for the people who are still considering the registration to help them resolve any problems. Okay, so let's speak about the other parts of the main user interface. If you click on the left top corner, you can open the left-hand sidebar. And this left-hand sidebar allows you to navigate to the entities, the list of entities that we just discussed, like materials, workflows, and simulation jobs. And here is how it looks when you open the account items. As we can see, there are materials, workflows, and jobs summarized for this account. The second component is the right-hand sidebar that can be opened by clicking on the top right corner. That usually shows the name of the account. And here we can access items like account preferences, billing and payments, and as well as open the web terminal and remote desktop. And there are certain entities related interface components as well that are not shown, were not shown yet in the previous pictures. And these entities related components include Explorer, or a table or a list of the items, a designer, a design environment allowing us to create or edit the items, the entities, and a viewer, a dedicated page allowing us to visualize the information about the entities. And I will review them in details right now. So this is how an entity explorer looks like for materials. This is the entity items list that shows the list of entities. And there are also toolbars for the actions at the top, and actions drop down for each of the entities. So if we select the drop down, we will apply the action only on one entity. Alternatively, we can select multiple entities here and select the toolbar action at the top. There's also a filter window here. Using this filtered space here, we can select specific items inside the list. So if you, for example, type SI, we also only select the items that contain silicon here. For the designer, that's how it looks like for materials. Again, it has multiple components. It's a entity-specific page, so it will look different for workflows, but for materials, it has 4 components. It has the header menu at the top, the list of items available inside the designer on the left, the crystallographic data panel number 3 here, allowing us to change the crystal lattice and basis, and the 3-dimensional interactive crystal viewer here to the right. It's a standalone JavaScript application that is also available as the open source GitHub repository on our webpage. This is an example viewer page for materials again. You can see the name of this material, its structure, the lattice and basis parameters, as well as tags, and whether or not it's public. So in the viewer page, we cannot edit the descriptive information, like the structure of material. But we can edit the information that we can adjust the information, including the name of the material. We can add tags and make this material public. Now a little bit about the accounts and sharing. Accounts are essentially human entities that can own and perform actions on entities. So once we created materials, simulations, or materials properties, we extracted materials properties, accounts own them and can perform actions on these entities. Accounts define different ways of how users can interact with the platform, and accounts have members, users that belong to them. There could be organizational, team accounts, and personal accounts. Personal accounts have only one member, the person or the user themselves. And the organizational accounts have different permissions on the entities. They delegate different permissions to different users. Account members have shared access to entities as set by the administrators of such accounts. There is a notion of collection of entities. And for each entity collection, we also create the entity collection bank. So to understand this concept, let's take a look at an example. We see that all the entities are collected inside the platform in a way that each account has their independent entities separately. So when I create a material under my account, I only see my materials by default. Now, unique entities from the account-owned collections are also collected inside a bank using a mapping operation. So when two people, when I create the silicon, the FCC as a material with 4.5 angstroms as a lattice parameter, and somebody else creates in exactly the same structure for silicon, then both of the structures will be mapped into a single entity inside materials bank. It has an exabyte-io property that we associate with the initial material inside the account-owned collection to show that it corresponds to this materials bank item. And there could be private and public data access scenarios. So if an account X here has private data enabled for it, then any entity that it creates inside the bank will not be accessible to any other account. And oppositely, when this account does not have private data enabled for it, the other accounts will be able to see the entities, the unique entities that this account creates. So for academic users, for example, usually it's not a concern when they work with, when they like to publish their work. So they prefer this scenario. Enterprise users usually like to be having their data private, like is demonstrated here. There is a curator's account that we associate the Exabyte team members with, or the people that help us curate the content inside the platform. So when you import the entities from the bank, like materials or workflows, we recommend import the entities that are created by curators first, because we curate them and we make sure that they're of high quality. So when you, for example, import entities from the bank, look for the entities that are created by curators account. Just like I'm demonstrating it here. So entity number 2 here is created by curators. Service levels is another concept that is important to understand to resolve the questions like pricing and the features that are available to the platform users. Service levels define the features that are available to accounts. And as you can see, we have four service levels identified here. Starting with the free usage, so we do not require a payment to be able to access the platform and use things like designing materials, designing workflows, and things like that. The first paid service is Pro, where monthly subscription fee is $10 or yearly subscription fee of $100 instead. Then there is a team account, team service level that allows multiple people to collaborate with each other within the same account. And then there is an enterprise service level that usually enterprise customers prefer because there's multiple people, there is an increased allocation for the computation that they use on a yearly basis and things like that. All of these service levels have the same compute price set for the ordinary compute type. Discussion of what an ordinary compute type is outside of the scope of this webinar, but essentially there are multiple types of computing. Ordinary is what we consider people are using most of the time. And sometimes there's other types of computing like GPU computing, for example, that we consider a premium type. And then there's also saving type of compute that is much less expensive than the ordinary, as much as 5 times less expensive, but it can be interrupted. So for all of these service levels, the compute price is the same. And then service levels also define the features that are available to account, like the availability of private data, as we just discussed in the entity bank conversation. And then how many members can be within the account, severity of the support, number of projects available, and other features like command line access as well. So let me summarize here about the core components. The data standards are at the very core of the Exabyte platform and define how it works with multiple entities through multiple access scenarios. These definitions are really meant as a unified format, so other people can pick them up and use them in their own work to make it interchangeable and connected with the Exabyte platform. The platform provides a user interface to work with the entities and gives alternative access options through the RESTful API, command line, or remote desktop. The accounts can perform actions on entities in a shared access way, allowing users to collaborate. And the features that are available to these accounts are defined by their current service levels from free to enterprise. Okay, so I'm done with the explanation of the core parts of the platform. Let's see if we have any questions. Looks like not. So let's continue and speak about the entities in more details right now. So materials first. This is how we can upload materials information into the platform. There's a quick video demonstrating how to do that. We click on the upload action in the toolbar to open the upload dialog. And then we click on select items inside this dialog window and select structural files. So here, structural files are available inside the dialog, but they are not yet imported. And we did that on purpose because sometimes people may want to import a large set of files, and they should be able to search through and edit and adjust these files and select them inside this model. So here, for example, what I'm doing, I'm tagging one of the structures. So I'm adding tag 1 and tag 2, comma separated entries here inside this menu. And we see that entry number 1 now contains tag 1 and tag 2 in the tags column. After that, I'm selecting all the items and clicking upload which finishes the upload of all this information into the platform. So now I have 3 materials added, and one of these materials contains the tags. So if I search for tag 1 here in the filter window, I will be able to see only this material. The second option for including adding material structural information is to import it from an online database. In this case, we'll use materials project. So we click on the import icon in the toolbar, which opens the import dialog. And here we can see that there are certain materials that we have already cached out of the total, the larger collection of materials within materials project. So about 3,000 materials we have cached locally on the Exabyte platform. I believe the materials project collection has much more, 40,000 materials available as of today. So we have access to all of these materials. And if I search for one of them, we will search the 30,000 materials, not the 3,000 that we have in cache. So we search for magnesium dioxide here. We select one of the entities that show up in the list, and we import it into our local collection. So again, there are multiple different repositories for materials data available to the users, and materials project is one of them. But instead of importing all materials at once, we let users tap into the larger repository and import only the ones that they are interested in into their private collection. Okay, just as we have demonstrated here. So we click on this entity, we open its viewer page, as I described before, that shows the structure of this material, the tags associated with it, its name, formula, and such. A third option for newly starting users to add structural information is to import or copy the structural information from materials bank. As we go and have more and more users, they create more and more materials inside the platform. So the likelihood that someone had already worked with your materials of interest is high as of this point. So when you're first starting, what you can do is navigate to the materials bank and search for the materials that you'd like to work with. For example, in this case, I'm searching for magnesium dioxide. And there was already someone who created material with magnesium dioxide as a formula. And I can copy that to my private collection. Okay, just like we demonstrate here. So we select the entity, we click on copy, and then this material item becomes available in my private collection. There is also a shortcut action to import entities from the bank, as we can see here, the blue action in the toolbar. Materials also support advanced search inside the bank or the personal collections. And advanced search allows us to search for more than just the formula. I have demonstrated how you can use the search by formula. It's a quick search. There are multiple other items that are available to filter and select and analyze the information inside the collection. So in this case, I'm using advanced search to set up a filter by formula and by the unit cell volume. We measure it in angstroms. So the formula that contains aluminum, the unit cell volume that is less than 80 angstrom cubed. And then I also select tags that contain high pressure. So this is the query that I'm running. And as a result of this query, I am extracting a single material, aluminum nitride, as I can see here. When I reset this query, I see the full list again. So that's how advanced search works for materials. Materials Designer can be accessed by clicking on the Create button in the materials list. And Materials Designer, as we briefly already discussed, has multiple user interface components: header, items list, crystallographic panel, interactive 3D viewer. And it allows people to work with material structures and adjust, edit them. So in this case, I'm demonstrating how one can select materials to work with inside the materials designer. Just a brief demonstration. There is a menu item at the top. Click on input output and then select the import option. And then choose one of the materials from the collection, the account owned collection. So I've just imported the aluminum nitride before. I was just searching for aluminum nitride before. So I'm selecting the same material and making it available inside the materials designer session. So by default, it starts with the default material, which is silicon FCC in this case. So when we fired the materials designer session, we started with silicon FCC. And when we added another one, we have two materials in the left panel. We can switch between the two. And we can also remove silicon FCC and work exclusively on aluminum nitride. So this is just a quick demonstration of what can be done with materials. Now let's proceed with the workflows and see what we can do with them. So just like with materials, when we copy the information from materials bank, workflows also have the notion of the bank and the bank collection. And as we go and proceed with developing workflows for the users and by the users, the collection of the workflows bank grows further and further. So what we can do when we are starting with the platform, we can navigate to the bank workflows. So open the left-hand sidebar, click on the bank and on workflows. And if there is a particular simulation that's of interest to us, we can search for it inside the bank workflows collection. So inside the bank workflows collection, in this case, I'm looking for band structure and selecting the item that I found in the list. And then click on copy to be able to have this item inside my account. So the band structure and density of state workflow now is also copied into the account collection. To be able to understand the logic inside the workflows and how it's executed, we have to speak about its inner structure. And the inner structure of the workflows contains sub-workflows. Here is an example flowchart that demonstrates a workflow. So this is a single workflow that contains two sub-workflows. And these two sub-workflows, they could correspond to a specific single simulation engine, for example, VASP or Quantum Espresso. And we do enforce that criteria by design. So sub-workflow can only correspond to one single application, but it can contain multiple different simulation units. And these units also can have sophisticated logic like branching inside them. The concept is introduced for modularity to be able to reduce commonly used logic. So in some calculations like density functional theory, we usually have a self-consistent field step and non-self-consistent field step, and then a post-processing step. And potentially post-processing can be executed by a different application, like some Python application, whereas the self-consistent step is executed by the simulation engine itself. So to be able to deal with this complexity, we introduce the notion of sub-workflows. Sub-workflows contain units, and unit is an elementary calculation. It is executed in a succession based on the logic included inside a workflow condition. For example, convergence, if-else conditions, and MapReduce. Units have different types. For example, there are execution units, like to run Quantum Espresso, pw.x. There are assignment units that assign a variable a equal to b. There are condition units that allow for branching. Execution units have executables associated with them, like pw.x, and they have different flavors, like self-consistent field, that calculation to be modular and reusable. So everybody can build a library of those different flavors. We provide templates, but again, they can be built by each account separately. Here is how the workflow designer looks like. At the top, we have a header menu that contains the name of the workflow and application used inside it. On the left, we have the items list sidebar. It contains the subworkflows. And in the middle, to the right, we have the subworkflow editor. So when we would like to add or delete subworkflows, we can do it as this video demonstrates. We click on the plus button in the subworkflow editor and select the option to append another subworkflow to the current. And as you can see, it shows up here on the left as a new empty subworkflow. Okay, and then we can delete this new empty subworkflow by clicking on the minus button in the subworkflow designer panel as well. So here, clicking on the minus button, we delete the subworkflow. Now, there are multiple different items included in the subworkflow editor too, like this actions menu bar, the editor tabs, and the units flowchart. The units flowchart demonstrate the logic by which the units inside the subworkflows are connected. And so if we click on one of the units, I can show it here, we will open the unit editor. One note before we do that is that the flowchart logic really has to look like a flowchart of a computer program. So in this case, we have a convergence flowchart where we set up a variable and then execute the calculation and then check the output of this calculation for completion. So that's how we execute the convergence workflow. So we check whether the output on this current step minus the output on the previous step is less than the threshold. And we consider the calculation converged if that's the case, and we exit and get the final value. If it's not, then we come back and rerun the calculation again. So this flowchart really today looks like this on the platform. It's work in progress, so there is a way to trace the logic, but it's not the most intuitive as of today. We'll keep on working on it and improving it. However, the important concept here is that there are multiple different types of units. Like A corresponds to the assignment units, like number of key points is equal to 1. C corresponds to the condition unit here. Condition, we will decide on branching and where to go after the condition unit. And the E stands for the execution unit, or PWSCF calculation, as shown here. Inside the unit editor itself, we can see information about the application, again, the executable and flavor for Quantum Espresso. We can see the properties that will be extracted after the unit calculation is done. We can see the monitor section. The monitors are extracted while the calculation is done. And we can see the next section that shows which item, which unit will be next after this one. And then we can see the input templates, the actual input text of the Quantum Espresso input file here. The important part about this input text is that we use templating language to be able to have materials information populated dynamically inside the text files. So here is how the template looks like. We can notice that there are multiple variables that are included in double braces. This is the Python or Jinja format that we use. And these variables can be substituted using the template data. So what happens is that we take the materials information and information about the workflow parameters, like the number of key points, key grid used for this calculation, and we pass this information to this template. So material information is passed to form the template data, and that, which is then passed to the template itself. And what happens is that we render the textual output with the material information in this case. That happens on the user interface, or as we call it, it's the first render on the web. However, when we post this file, it still contains some variables that are not substituted. And the second substitution happens during the runtime on the computational infrastructure. It really is not a concern for the users what the job working directory is going to be called. This is not something that they should be worried about. And that's what our infrastructure automatically substitutes during the runtime. When we do something like convergence, we also have a certain convention that we use to be able to create multiple directories to run multiple calculations for the convergence workflows. And again, that is automated. It's not a concern for the user. It's been substituted at the runtime level. Okay, so the important concepts for the workflows and materials we have covered. Now let's proceed to the jobs. We're running a little bit over time, so let's focus on the important parts here. To be able to create a single job, one has to create the materials, create the workflows, assert that the account has enough balance to perform these calculations, and assert that we have enough disk space to perform this calculation. Then we navigate to the desired project, or we can select Create Job, shortcut in the left sidebar to use the default project. Now that's how the job designer looks like. There's a Materials tab, Workflows tab, and Compute tab, as well as the header menu that contains additional drop-downs for the job actions. This is the Compute page. It contains time limit, the cluster, the queue, nodes, and number of cores. Let's start with the selecting of the materials. So here I'm clicking on the drop-down and the header and choosing Select Materials action, and then selecting multiple materials to be passed to the job designer. So what happens is that all these 6 materials that I selected are now present inside the job designer. And you can notice that inside the name of the job, we can see this formula variable, very similar to the ones that we just discussed inside the template. So this formula will be substituted with the materials formula upon the job creation, which means that we will be creating 6 different jobs out of the single job designer session. The second step is to select a workflow. Workflow can also be selected, we can only select one of them. Again, we click on the drop-down, select one of the workflows that we've previously created, and as we can see, it shows up in a job designer session. The last step is to set up the computational parameters, and this is a separate topic for the discussion, how to choose the computational parameters for what calculations and what's the logic for it. In this case, we'll just keep them by default. By default, we're using the debug queue, so 1 core and 1 node as well. Then we click on the Save button that looks like a check mark to save the job. And then we're done, the jobs are created. A couple of notes, workflows cannot be modified during the job creation by design to simplify the user interface components and to assert the data consistency. Users should modify or edit the workflows first and then select or modify the workflow during the job creation. So when there are big adjustments to the workflow that change its logic, those should be executed inside the workflow designer. When there are small adjustments like changing the number of K points or something like that for density functional theory calculations, they can be done inside the job designer directly. The unit input preview can be edited directly inside the job as well, but we do not recommend doing that because the consistency and the parameters of the workflow are then lost. The data, the metadata that contains the parameters of the workflows is then replaced by the edited text. Multiple materials can be selected for the high throughput type calculations, where multiple materials create multiple jobs, or multiple materials can be created, can be selected for multi-material calculations like NEB, chemical reaction workflows, and such. Jobs can also span other jobs and wait for the execution, but that's a topic for a separate discussion in advanced topics webinar. Once we created the job, we can run it. like this video demonstrates. Select the job item, click on run, and it goes from the pre-submission state, which is this light blue, to the dark blue submitted state, and then to the active in orange, as we can see here. And then we can track the progress of the job. We can navigate into it, see how it progresses, click on one of the units, see the output, and see how the charts, the convergence charts, are evolving over the time. And finally, when the calculation is done, it starts to turn green. F means finished. So we can see and navigate into the job to see its result. Note that there are two extra tabs now available, the results tab and the files tab, and they contain the results and the files accordingly. Okay, so that's about it. I think this is the explanation of the basics of the Exabyte platform. Again, we spoke about the core items. We spoke about materials, workflows, and jobs, and the actions that we can perform on them separately using the information from the core items discussion. So let's see if we do have any questions this time. We have time for one short question, let's say that. Okay, looks like no questions at this time. If that's the case, then I'd like to thank everybody for their attention. And I'd like to conclude our session on this. Our next webinar will be at the end of December 27th. We'll send out the invitations to everyone. We'll send out the invitation in separate emails. Again, thanks everybody, and looking forward to seeing you again at the Advanced Topics webinar.